All right, welcome everybody. My name is Dion Rossiter, and I am the Executive Director of Science at Cal. It is so great to have you for our June Midday Science Cafe, our collaboration with the Berkeley Lab. We have today, can we make green hydrogen fuel a reality? We have two doctors presenting today, Dr. Julie Fornaciari and Dr. Arthur Diaz. So thank you one more time for being here. As usual, we're going to start today's program with a land acknowledgement. We acknowledge that Berkeley sits on the Huchun territory, the ancestral and unceded land of the Ohlone people, the successors of the historic and sovereign Verona Band of Alameda County. This land was and continues to be of great importance to the Ohlone tribe and other familial descendants of the Verona Band. Every member of the Berkeley community has and continues to benefit from the use and the occupation of this land since the institution's founding in 1868. By offering this land acknowledgement, the Berkeley community not only recognizes the history of the land on which we stand, but also recognizes that the Ohlone people are alive and flourishing members of the Berkeley and broader Bay Area communities today. So thank you for allowing me the chance to give that land acknowledgement. As usual, we have upcoming programs we'd like you to be aware of. We have CRISPR 101 on July 21st, and we have Material Science for Sustainability on August 18th. So we hope that you join us then. Mark your calendars. You will all be getting emails about those upcoming events soon. So what is Science at Cal? Well, in 2008, Science at Cal was envisioned as a unifying effort to raise public awareness, understanding, and appreciation of the scientific research happening at UC Berkeley. To realize this vision, we engaged the vast Berkeley science, technology, engineering, and mathematics community, that's STEM, as science communicators and foster creative collaborations among campus and community-based groups who share our commitment to equity and inclusion in STEM education and in careers. Science at Cal connects UC Berkeley STEM researchers with diverse groups of all ages, backgrounds for science engagement and learning. Accessibility, inclusiveness, creativeness, and innovation are hallmarks of Science at Cal events, which reach tens of thousands of people annually. And throughout the years, we present ongoing, always free outreach programs for STEM and other disciplines, which help promote other groups related efforts like consulates and libraries. And First Friday, you can see all of our partners here. And all these initiatives, we bring them to the community for free. This is a broad scope of activities is made possible through our dynamic work of campus alliances and valuable community partners. So I encourage you to go to our website. We already have a question about this talk being available for viewing. And that always reminds me to let you all know that yes, this talk is being recorded, and yes, it will appear on both Science at Cal's and Lawrence Berkeley Lab YouTube channels, and we will send that out after the program once we get them online. Maybe someone in the chat can respond with both of our YouTube channels in case you want to follow us, because we have a lot more content than just the Midday Science Cafe programming. I also want to mention that you have an option to see the closed captioning. If you click your three buttons that say more, you can see closed captioning options for this talk as well. So with that, I will hand things over to Jen Tang from Berkeley Lab. Thank you.
Thanks so much, Dee. So hi, everybody. I'm Jen Tang. I'm the Director of Community Relations at Lawrence Berkeley National Laboratory. And for those who aren't familiar, Berkeley Lab is one of 17 U.S. Department of Energy national laboratories across the country. We're supported by the Department of Energy's Office of Science, and we're managed by the University of California. All of the research we conduct is unclassified. Now, since our founding back in 1931 by a UC Berkeley physics professor named Ernest Orlando Lawrence, we've been dedicated to advancing the scope of human knowledge and seeking answers to some of the greatest problems facing humankind. Today, Berkeley Lab employees work together to develop meaningful scientific solutions to the world's most intractable energy and environmental challenges. We help train the next generation of scientists and engineers, and we make sure that those things happen in a manner that benefits everyone. Our main campus is located in the Berkeley Hills, and our close ties to the UC system create a really unique and synergistic environment for scientific discovery. A number of the lab's researchers are affiliated with one of the UC campuses, either as students, postdocs, or professors, many of whom have a joint appointment here at the lab. And we're especially fortunate to have a close relationship with UC Berkeley, and our institutions joined forces across a number of scientific frontiers. And one of the main motivations for creating the Midday Science Cafe series is to share with you examples of compelling and complementary scientific research that are coming out of both of our institutions. So we hope you enjoy today's presentation on green hydrogen. And with that, I'm going to ask Dee to stop sharing her screen, and I'm going to introduce our first speaker. And it is my pleasure to introduce Arthur Dizon. Arthur is a postdoctoral researcher in Berkeley Lab's energy technologies area, and his current work looks at the development of continuum multi-scale mathematical models for hydrogen energy technologies, with a focus on systems using proton exchange membranes. And don't worry, Arthur will explain what those are in his presentation and how he uses these models to inform design and optimization efforts for green hydrogen. Prior to coming to the lab, Arthur was at the University of Florida, where he received his PhD in chemical engineering. And in his spare time, he likes to play guitar, go biking and hiking, and spending time with his family. So with that, Arthur, I'm going to ask you to turn your camera on, and I will hand things over to you.
Thank you so much for the wonderful introduction. And today I want to talk about my work, primarily focusing on mathematical modeling and how we use that to advance hydrogen energy, an upcoming technology that we're hoping will advance and help our environment. So let's see, click forward. All right. So we're all familiar with how greenhouse gas emissions influence climate change. And a brief summary of that is that we generate greenhouse gases from human activity, which build up in our atmosphere and then cause climate change due to the trapping of the energy, solar energy. So if we just look at greenhouse gas productions in the production in the US, you could see that there are large segments that produce a lot of greenhouse gases, primarily transportation and electricity generation. If we dig into this a little bit more, we see that 73% of our greenhouse gas emissions come from burning fossil fuels. And a majority of that is CO2. So what we're working on is developing an electrochemical solution for specifically the transportation aspect of greenhouse gas emissions. So we are all familiar with our current internal combustion engine. You fill it with gas and the car goes, and that is what we have, very common ubiquitous technology nowadays. We are working on developing electrochemical solutions to this, primarily electric motors are significantly more energy efficient, and then in the process of generating motion, we don't produce greenhouse gases. So we're familiar with battery technology, where you have an onboard energy storage device to power the car. The advantage of this system is that we have a well-developed electrical infrastructure, but this technology suffers from long charging times and the resources associated with making the batteries and also the waste generated in that process. Our solution is using hydrogen, where it's an onboard energy conversion device, where we load up our car with hydrogen gas and react it with oxygen in the air to make electricity and emit water as our byproduct. The advantage of this technology, it's a quick refuel time, similar to gasoline, but the problems is that we have no infrastructure for this technology currently, or very little, and then the production of hydrogen is not a green process, where we still derive most of ours from fossil fuels. So this is a graphical representation of a fuel cell car, a proton exchange membrane fuel cell car, which is a specific implementation of hydrogen technology. And the proton exchange membrane is just a selective barrier that allows protons to pass. So on the right, you'll see a representation of a hydrogen fuel cell. And then the membrane is sandwiched between two electrodes, which is where our electrochemical reaction occurs. So we introduce hydrogen on one side of this fuel cell and then oxygen on the other. And then these two then go react to produce protons and electrons, which the electrons are used to drive the electric motors. And then they recombine on the other side with the oxygen to form water. So in developing this technology, we have to have an understanding how this fits into the global energy, or at least the national energy landscape. So these graphic represents how hydrogen will fit in and how it will be produced. So on the left side, it primarily concerned with hydrogen production. And on the right side, circled, it's how we use and utilize hydrogen. My work is primarily focused on how we use hydrogen. So if we focus on this bubble, this represents our hydrogen supply. And then these smaller bubbles around it with the arrows represent how we use the hydrogen. And as we discussed, that transportation is the focus areas that where we want to target this technology for. And transportation is broken up into several segments, one being a light duty application, which are like passenger vehicles. And this technology is already out there, and we're just waiting for this infrastructure to grow around it. The work I'm doing is focusing on medium and heavy duty applications of hydrogen fuel cells, which include larger passenger vehicles and even airplanes, container ships, and semi trucks. So this graph on the right represents the benchmark durability measured in millions of miles of how long these fuel cells need to last on the road or in the air. So you can see that for light vehicles, it's 150,000 miles is the expected lifespan of these fuel cells. But for medium and heavy duty, require significantly more, 500,000 up to 1 million miles, depending on application. And so this is where my research fits in, is that how do we increase the durability of these fuel cells? So I primarily focus on developing mathematical models. And then the mathematical model is just a representation of the physics and chemistry that occur around it. So as a history of mathematical modeling, I like going back to Sir Isaac Newton, who famously observed an apple falling and then came up with a model, pretty much force equals mass times acceleration, a mathematical model to describe motion, which was then used as the basis to describe planetary motions, comets, and tides, and pretty much a lot of the stuff that we a lot of the physics and science that we see now. So I use the same approach, but I use mathematical modeling to describe fuel cells. So there's several different scales that we can model in a fuel cell. One being microscale, which is atoms, molecules, and particles, so very small things. A cell level model where you see this is an image of a lab scale PEM fuel cell, and a graphic of it opened up. And then also a system level model, which shows the full integrated system and how that whole system would perform. My research is primarily focused on cell level modeling, so pretty much a small cell that is what we use to study. I use to model. So in doing this modeling, I perform it in using what we call a continuum model, which consists of a large set of partial differential equations. So a lot of mathematics, and they basically look like this. I'm not going to describe all the terms, but they represent the physics that are going on in the system. And then they represent all these aspects that we have to consider when we're developing these models. One aspect is multi-phase, is where within a fuel cell, we have a liquid phase, gas, and solid, and they all behave differently. And so we have to account for the physics associated with each phase. And even with our gas phase, we have multiple components where we have hydrogen, oxygen, water vapor, and nitrogen from the air. So the additional physics that I account for is, things like equilibrium thermodynamics, which describe condensation and evaporation of water, reaction kinetics, pretty much how we form protons from hydrogen and then reform water. So describing the rate of those chemical reactions, which are shown here. And then fluid dynamics, how those individual liquid and gas phases flow. And also heat transfer, pretty much the heat generated in our fuel cell, how it describes how that heat is dissipated. So now we have a bunch of equations, and then now we need to solve them. And then my primarily utilized method is a finite element method, where we break up our equations into little bits called into finite elements. So this is the picture of a fuel cell, which I showed earlier. And if we open it up, we'll have two halves, one being one electrode and the other. And then so if, and the one side both sides have a flow field, which direct the flow of gases, which is this little groove channel right here. And then we insert our membrane and electrode between these two. And then those gas channels allow the flow of gas supplied to each side of the fuel cell. So if we look at a cross-section view of this fuel cell, you see this kind of profile with these channels and flow fields. And if we zoom in and zoom in again, this is the modeling domain that I typically utilize, where we have gas channels and then our flow fields, and then in between is our membrane and electrodes. So this is an example of an output from one of my models, where we can see the temperature distribution in Fahrenheit of an operating fuel cell, or a theoretical operating fuel cell, where we could see the generation of a hotspot in our membrane due to the electrochemical reactions. And then we also have fuel cell concentration of gases, gas species. And then also we can generate a power curve where we can see where is our optimal power output as a function of operating current. So these are examples of what I'm able to generate with these models, and how these, and this information is what we use to optimize and design for the fuel cells. And then in the end, my goal is to make models that are better. And then the question is, what is better? What is better is that making models that agree with our experimental data. And if they do not agree, we have to add physics or refine the physics by adding better representations of each component within the fuel cell. So this is an example of one thing that current research that's going on. And then once we have these better models, we can scale them up into system levels, and then integrate that into better representation of how the hydrogen economy works as a whole. So overall, I just want to thank the Berkeley Lab in Berkeley and our support from DOE. And that's it. Thank you.
Fantastic. Thanks so much, Arthur, for that great presentation. I'm going to ask you a couple questions before we hand things over to our next speaker. So, the first question I have for you is, what's being done to improve the creation of hydrogen infrastructure right now?
Yes, there is a large push by the DOE. It's out in the news. It's available of pretty much strategically installing infrastructure in the U.S. So certain aspects are focusing on shipping lanes. So then these high traffic route for cargo for like semi trucks is one of the current plans, in growing it from there. So focusing on the heavy duty applications, because they follow along certain paths. And then, so then they have several initiatives, Hydrogen Shot, and then consortia that I'm a part of with other national labs and other universities. So it's focusing on where we could utilize those heavy duty applications, and expanding from there is the current focus.
Got it. Thanks. And so I'm also going to ask you a question that we got from our audience, which is, what's the most efficient way to use hydrogen for transportation? Is it, the fuel cell electricity generation approach, or is it actually something more like direct internal combustion as a replacement for fossil fuels?
From my understanding, and the efficiency of hydrogen fuel cells really comes into the efficiency of that electrical motor. And combustion is on the order of 25% energy efficient. So you dissipate a lot of it in terms of heat. So the advantage of an electric motor is that they are significantly more, the numbers I'm throwing out, I think is like 80, 90% a lot more energy efficient. So that's where you save a lot on utilizing hydrogen electrochemically rather than as a combustion source. So that is the best utilization. So once we get the infrastructure around it, then just like electric cars and having the charging stations, the infrastructure needs to catch up to the actual technology. So that is the advantage of using hydrogen electrochemically. It's just the efficiency associated with those motors.
Got it. Thank you. Well, thanks so much for your presentation. I'm going to ask you to stop sharing your screen, and I'm going to invite Dee up to join us, where she'll introduce our next speaker.
And I am going to invite Julie up to join us. And you can start sharing your screen, Julie. So Julie Fornaciari just completed her PhD, so congratulations to her, in chemical engineering at UC Berkeley. Go Bears, under Professor Alex Bell and Dr. Adam Weber, where she focused on electrochemical energy conversion and storage of hydrogen gas. She has spent the last 5 years understanding how to make hydrogen gas from water, i.e. green hydrogen, and has studied how to make them more efficient, use the technology as a platform for different chemical reactions, and how to use the technology in specific applications. Julie is a first-generation college student from Chicago, and in August, she'll be joining the Department of Energy as a Hydrogen Shot Fellow in the Hydrogen and Fuel Cell Technology Office in Golden, Colorado. In addition to her research, she is really interested in science communication, so I'm so happy she's here, and bridging the gap between scientists and non-scientists. She has volunteered for various programs through the nonprofit Community Resources for Science, including the Bay Area Scientists Inspiring Students, or BASIS program, was a writer and editor for the Berkeley Science Review magazine, and has served on the programming committee for ComSciCon flagship conference for the past 2 years. She's also a loyal volunteer for Science at Cal. I'm going to plug that into your bio, Julie. And outside of science, she loves to read, hike, rock climb, camp, travel, and pet all the dogs. So don't we all? Julie, it's so great to have you, and I will turn things over to you.
Thank you so much, Dee, for that introduction. And yeah, I'm so happy to be here talking about hydrogen, and Arthur gave a great start to this presentation about green hydrogen. So today I'm going to talk a little bit about transforming water to green hydrogen. And first, we're going to talk about how hydrogen gas is being currently made. So we talked about an application in fuel cells with Arthur, but we're going to talk about how it's made currently and why that might be a problem. Additionally, we're going to talk about green hydrogen, what it is, how do we actually make green hydrogen, and why is it a solution to the problem. And then hopefully I will give you some ideas of what I do with my research, or what I've done through my PhD, and how do we implement green hydrogen to the world through different aspects and questions that we try and solve through our research. So how hydrogen gas is made currently is we have a big chemical plant that is pretty centralized, it's big. And we have natural gas feeding into it, and then through a process we get hydrogen gas out, where we can then feed it into our fuel cells. This process is called steam methane reforming, which really means we're burning that methane at really high temperatures, and we get hydrogen gas out, but we also get carbon dioxide. So while those fuel cells don't emit carbon dioxide like an internal combustion engine, we do get carbon dioxide when we make hydrogen. Which is a problem, since we want to be able to reduce carbon dioxide emissions throughout a lot of these processes. But this isn't the only way to make hydrogen gas, and so we're going to talk about a few ways that we can make it. This way that we just talked about is gray hydrogen. So the dirty hydrogen, if you want to think about gray as maybe a little more dirtier. We also have blue hydrogen, where we feed in natural gas, and instead of allowing that carbon dioxide being emitted to the air, we trap it, and that can be either through some sort of technology, through carbon capture, or we put it into the ground, but otherwise it's not going to be coming into the atmosphere. And so that's called blue hydrogen. The other two ways we're going to talk about is a little different of a plant, where we're going to use water, and we're going to just coin it as a hydrogen plant for now. And yellow hydrogen is where we take electricity from the grid, which we also know depends on fossil fuels to generate electricity. And then we get hydrogen gas out. So we know that CO2 may be emitted because we're still being dependent on fossil fuels, but we're not being dependent on fossil fuels directly for hydrogen gas. And then the last but not least, which is why I'm going to be talking to you all today, is green hydrogen. So really utilizing electricity from renewables, so from solar or from wind turbines, and generating hydrogen gas from just water and that electricity from that renewable energy. And so these are just a couple ways of how to generate hydrogen gas. And we use, for those yellow and green, a device called an electrolyzer. And an electrolyzer is really a device that takes in water and electricity, and you can get out hydrogen gas and oxygen gas. And it can be operated, if you want to think about it, like a battery or like the fuel cell Arthur talked about, and you'll see we have a lot of similarities. At 2 electrodes, so you have a positive end and a negative end for these reactions to be occurring. So with what a water electrolyzer is and makes that hydrogen gas, I want to take a step back and revisit the figure that Arthur went through as well, where we're looking at really the, how hydrogen gas is being made, and hydrogen, is used in a lot of different things. It's not just used in transportation. So hydrogen is made through lots of different ways. I didn't even mention nuclear, but that's another way we can make it. But we can do it with renewables, fossil fuel, or gas infrastructure. And we have, a supply of hydrogen gas available. We can then, use that as a power generation tool to go backwards. And then we have lots of different applications like Arthur talked about. So the transportation is just one. But if we can generate hydrogen gas and eliminate this gas infrastructure or the fossil fuel dependency, we can then start making a lot of different processes and start reducing how much carbon dioxide is being emitted, from the process of fertilizer or chemical processes. And this is really what we think about as deep decarbonization. So going earlier on in the process and removing carbon through the earlier steps. And hydrogen is one way to do that. So this is important to look at it. So for this hydrogen generation, we're going to talk about it in a very simple way right now is, how does this occur? So green hydrogen, like we said, has to come from renewable energy. And we use 2 electrochemical reactions that Arthur luckily already introduced. So really electrochemical reactions I always think of as, electricity, electrons, and then chemical, which is breaking of bonds. And so if we have these 2 electrodes here, we could feed in water and electricity. And when they react at those electrodes, we then get oxygen and hydrogen out. So we can, see that hydrogen will come out on one electrode and oxygen will come out on the other. We'll go into a little more detail of how that works too. But this is really what we think about for green hydrogen. It's 2 electrochemical reactions happening simultaneously. But, what does this electrolyzer look like? I'm not just putting in 2 electrodes into water. How can I use this in my system or in my real world? So an electrolyzer, this is the overall schematic, right? But it could look like something like this, which if you've taken a Gen Chem course or if anyone has seen Gen Chem courses or laptop courses, you could have just a cup of water and you can have some pencils or you can even do spoons.
Hey, Julie.
Yeah.
Can I interrupt you and just ask, there's been a request for you to just speak a little slower so that the closed captioning can pick it up a little bit better.
Oh,
I think
my
you're
apologies.
yeah, no. You're speaking at a great pace. It's just that maybe slightly slower.
Perfect. Sorry.
Thanks.
My apologies. So yeah, so this is just one example where we could have a cup of water, right? And we can have 2 electrodes that are made up of pencils, or we can make 2 spoons, attach it to a battery. We would need some salt. So for electrochemical reactions, we need some electrolyte. And we can actually see bubbles being formed. And that is our hydrogen gas. And I actually did this with the after school science program that Berkeley Lab hosts just a couple weeks ago. So this is one example of an electrolyzer. It could also look a lot like this, where it's a larger plant, right? And it looks a little bit more what we think of as a chemical plant. This one particularly, we have a storage tank for hydrogen, and it produces a lot of hydrogen. This system, though, really likes to operate 24/7. So when we have intermittent resources like solar or wind, it's going to become an issue if we shut this system down or bring it back up so quickly. So another option that we can do is the one that I work on, and it is very similar to some of what Arthur talked about, which is what we like to call is an electrochemical sandwich. So this is a lab bench cell. So this looks familiar because Arthur works on very similar ones for fuel cells. And this lab bench cell is just a small one that we can test to run different electrochemical diagnostics to better understand it. And this electrochemical sandwich is really just as thick as a couple pieces of paper. And it really depends on a barrier that you want to think about as like the meat of the sandwich, which is our membrane. And that's the same membrane that Arthur spoke about, which is the selective membrane that allows hydrogen atoms or protons to move through it. So this is one way where we can, turn this system on and off pretty quickly and still be able to generate hydrogen when we have solar available to us or wind. But within these electrodes, what I've worked on in my PhD is these electrodes contain catalysts. And catalysts are just metals that help the reaction proceed. And we wanted to consider with these systems is how do we make hydrogen, how do we make more hydrogen with, say, less catalysts? Because catalysts can be really expensive. We also want to take into consideration how can we make them more efficient? Can we change the way that electrode looks or how it's formed? And so those are some of the questions that I've asked during my PhD. And so with this, here are some pictures from me in lab with one of my old lab mates, where we're actually making one of these electrochemical sandwiches. So we use basically a spray gun or a spray coater to put those catalysts down on one side of that membrane. It doesn't look as tasty as a sandwich, for instance. It's just kind of a black square on a membrane, but this is actually where the hydrogen and oxygen will be formed when we put it into that cell. Additionally, we do other diagnostics before we even start doing any electrochemistry. So this is another machine in our lab where we put in our electrodes and figure out how well did we spray coat it? Did we put enough catalyst on it? Did we put too much? Did we ask those questions to get an idea of just how much of the catalyst is available for the reaction? And then we run electrochemical tests, try to understand were we able to achieve our goal or not, other questions like that. And kind of leading into that, what still needs to be done within hydrogen generation is, the cost of these systems are high. That's kind of where my PhD kind of went in, is how do we make these more efficient while reducing some of the catalysts or, reducing the metals in that electrode. Additionally, since these systems have to run, they have to get turned off when we don't have sun, turn back on when we do have sun, or wind turbines when it becomes windy or not windy. We need to make sure that they last a long period of time during those turn-ons or those startups or shutdowns. And so the lifetimes of these systems needs to be improved. And that's an active area that our lab is looking at to better understand how to make these systems a little more, for these systems to last a little longer. Additionally, like Arthur mentioned in his question, infrastructure needs to be built. So not only do we have to have the infrastructure for hydrogen gas to fill up those cars, but we also need infrastructure to be built to make these systems, because right now the way that we do it right now is feeding in natural gas and making hydrogen gas that way. And then also we try to find and be creative and find the most advantageous applications. One project I worked on specifically was using actually that same device that I showed you earlier and run it. So we had to change a couple things, but run it both as an electrolyzer and as a fuel cell. And so you could see as one example, we could have, hydrogen being made when we have too much electricity being generated, when it's a beautiful sunny day like we've had in the Bay Area. And then we can make a bunch of hydrogen and store it. And then once it becomes dark out and we need electricity, we can then use the same device and just run it in the opposite direction and run it as a fuel cell where you can actually generate electricity that way. So that's just one example of one of the applications that I worked on specifically. And so I just want to say thank you all, and I'm happy to take any questions.
Thank you so much. That was wonderful, Julie. So we will take a few questions before we open the Q&A up to Jen and Arthur. But so first question is, how expensive is hydrogen currently? And what is the goal for green hydrogen really?
Yeah, so right now with natural gas, the price of green hydrogen is, or price of hydrogen from natural gas is about $2 per kilogram. If we try to make it with green hydrogen as of today, green hydrogen is around maybe $4 or $5 per kilogram, and that might actually be a little optimistic. The goal, though, is through the Department of Energy, actually, they released it last year, that they really want to hope to reduce the cost of green hydrogen, so through the electrolyzer, to be $1 per kilogram, and they're trying to achieve that in the next decade. And that's actually what my fellowship that I'm going to be joining is named after, which is the hydrogen shot. So that's the goal that we're trying to aim towards, to do $1 per kilogram of hydrogen in 1 decade.
Got it. Thank you. Makes sense. And maybe we'll invite you back after a year or two to learn more about what you're doing. That seems so exciting. So is the electrochemical sandwich that you showed the only sandwich that exists?
Yes, that's a great question. I'll go back to that really quickly. So this electrochemical sandwich, like we said, moves protons through the membrane. There is an active area of research that actually moves hydroxides, so oxygen bonded with hydrogen. So in basic conditions, this is in low pH acidic conditions. If you think of like lemons, we'd actually do it more in the basic conditions if there's oxygen bonded to a hydrogen and we transport that. And that's advantageous because we could use a lot more different catalysts in those electrodes. And we could use cheaper catalysts as well. So that's actually an active area of research that's being done to try and understand if we switch that pH, make it closer to something like bleach, can we run this in the same type of sandwich configuration?
Excellent. Let us invite both Jen and Arthur up to the screen. So thank you for stopping your share screen. And Jen, why don't you go ahead and ask a few questions?
Sure thing. And I'm going to wait for Arthur to turn his camera on so he can join us on screen. There he comes. So I think I'm going to start with this question, which maybe both of you can talk about, but can we talk a little bit about the safety of hydrogen? It's highly flammable. Thinking maybe about the Hindenburg. Can you talk just generally about the safety of hydrogen in I guess both making it and in applications?
Well, yes, the safety aspects of hydrogen, like if you compare it to like gasoline right now, like the lower flammability of limit is a number that they experimentally calculate or measure. So like how much gasoline, what is the minimum amount of gasoline vapor is required in air in order to be combustible? So gasoline is around 1.7% gasoline vapor to oxygen. For hydrogen, it's up to 4%. So you also have some buffer there. So then it requires lower concentrations of gasoline vapors to be flammable. And if you have leaks, there's also rapid dilution because you're also under a pressurized vessel. So there's a lot of work that's been done about making hydrogen safe for these type of vehicles. So that is often the concern about leaks of hydrogen, and isn't it flammable, combustible? And yes, but is it more or less combustible than our current technologies? Right now it's a little bit less. So but that is always a constant focus on making sure that these things do not reach concentrations that are dangerous. And so that is always a focus in developing these technologies.
Yeah, and just to echo that, I think that's the biggest part of it, is like the safety culture around hydrogen is so big that we know it could lead to something like a big explosion like the Hindenburg. We hope that doesn't happen again. And so really making sure you put in those safety nets to make sure it's shut off when it needs to, and things like that is really important. And like Arthur said, we're comfortable with our combustion engines because it's what we know, and because there's a lot of safety around it. And that's kind of the culture that we are kind of building through hydrogen too, is making sure it has all those safety elements. So it's just as safe as, you know, being on a jet fuel, like on a plane with jet fuel, or being in your car.
Thanks both. And maybe just a follow-up question for Arthur around safety. So how's the hydrogen safely stored in vehicles? Is it like a metal hydride absorbent type of technology, or is there hydrogen in like a tank?
Not too familiar with those. So as I said, like a lot of my work is focused on like cell level modeling. So integration into the whole system, I'm not as familiar with, but I do know and familiar that there's a lot of different technologies of trying to efficiently store hydrogen. So I've heard of those metal hydride as an option in other type of materials. So I mean, that's just my focus and area of what I do research in, is not really like how we store hydrogen, but I just know it is an active area of research, how to safely store it and properly store it, and to get the most efficiency in storing it, because those tanks can be heavy, and so and as I said, it's all related to a safety aspect of utilizing hydrogen for energy.
Got it. That makes sense. Thanks, Arthur. So actually, I just saw a question that came in, and I was pleased to hear, Julie, that you're going to be heading over to the DOE hydrogen office to help with the hydrogen shot. Somebody wanted to know, is there, I think, a Twitter account or like a place where people could learn a little bit more about the hydrogen shot?
That's a great question. I don't know it off the top of my head, but I'm pretty sure there is. Let me look it up really quickly on my Twitter, and I will share it with all of you.
All right, we'll have Julie drop that into the chat.
Elise added it into the Q&A, but maybe Elise, you should add that into the chat box so that everyone can have that information, if you don't mind. She did put the Twitter account and the Facebook account and the website up there. So
thank you.
As a response.
Sounds good. Dee, why don't I hand things back to you for a couple questions?
Sure, since I'm already butting in. Okay, so many microbes have evolved to efficiently break down biomass to produce hydrogen. Why isn't this method under consideration?
Yeah, so that's a really good point. And it is under consideration. So I know very little about bio and how to do this, but I find it really interesting. But I only showed just a little snippet of what is similar to what I'm working on for, you know, my electrolyzer. But there's lots of different ways to do it, like biomass, or they're even looking at direct using solar. So that's called photoelectrochemical systems. So they look a little different, but trying to use solar energy and like a solar panel almost integrated into these systems. So that is 100% being considered. A lot of these things, they look at technology readiness level. And so I showed kind of a like higher technology readiness level that hopefully we could, you know, see in our day-to-day life soon, where the biomass is a little bit earlier on. So it's not as ready to get into large scale. But 100% right, that is one way to make hydrogen. And there's some really interesting research coming out with it.
Great. So folks are working on it. It's just not quite at the point where we're scaling up. Excellent. All right. Thank you so much. So what are the benefits of using the same device for both an electrolyzer that came out very hard during the day and a fuel cell at night? What if you need electricity during the day?
Great point. So you definitely could run it as a fuel cell during the day too. So it's not just limited to like, okay, it's nighttime, like switch it off to a fuel cell. But one advantage to it being one device is it reduces how many parts you need to worry about when having, you know, maybe a separate fuel cell and a separate electrolyzer. So it's a much larger system. We coin it as kind of balance of plants in our sciencey terms, which really is just kind of what else do we have to integrate into our system. So having it in one device helps it really, you know, streamline the process, and it's just kind of a flip of a switch that we would be able to run it in one direction. So the electrolyzer direction, you need water too, but then also flip it into the fuel cell. And there's definitely interesting research that's happening with how fast can they switch between these modes. But you would need enough hydrogen in order to get enough electricity that you would need. that's kind of the limitation. So if you need electricity during the day, maybe a battery as a supplemental energy or electricity source would be a good use of that. Or if you have solar panels, you can use it both as hydrogen, but also electricity during the day. Hopefully that makes a little sense.
Yeah, helpful. Thank you.
All right, so I'm going to toss a couple of questions Arthur's way. Can you talk a little bit about the efficiency of fuel cells? So for example, are fuel cells any less energy efficient than, say, like a plug-in electric vehicle, especially because, of the energy that's needed to create the hydrogen? So can you talk about whether or not that's true, or whether there might be any leakage of hydrogen during storage in a vehicle?
All right. As far as efficiency, they utilize the same electric motor. We're all using electricity as a conventional battery car. So efficiency, as far as mechanical efficiency, you're pretty much looking at the same at that point. The real losses, as you stated, it's really in the generation of sufficient amounts of hydrogen, because in order to fully implement these type of vehicles, we're going to have to make a lot of hydrogen. And that's, what Julie's work is focused on, is that how can we cost effectively produce the amount of hydrogen that we would need. So I've heard references that, it's a good transition fuel, hydrogen is, because currently we can make it using steam methane reforming, but, in the long-term goal is finding another source. So efficiency-wise, I think there's no difference between an electric motor driven by a battery or an electric motor driven by a hydrogen fuel cell. And if we do have leakage, yes, you have, just like a fuel leak in your car. If you're losing gasoline at your car through a leak, yes, that's an efficiency loss, a utilization loss. So, at that point, it becomes the better design that we create vehicles and containers that don't leak.
Got it.
Or have minimal leaks.
Right.
So it's really just in line with what we see with battery vehicles, and then also you have the same problems with current internal combustion as their fuel source as well. You have leaks there as well. So.
Got it. That's helpful to know. A couple more questions about hydrogen vehicles. So do you know how many miles a typical car can run on, let's say, a kilogram of hydrogen?
I do not know directly on how much they run. I'm just not familiar with how much kilograms of hydrogen they're required to fuel a fuel cell. I'm sure that information is available online, so I could look that up. But I know that they design these commercial vehicles. So like Toyota has one, Hyundai has one, and they aim to be on par with the mileage that you expect out of a normal combustion engine. So you're looking around 300-400 miles, around that 300-mile range. Mm-hmm. So on a fuel up of hydrogen, you get about that same rate. And I think, if I recall correctly, but hydrogen, I think all the hydrogen refueling stations are in the Bay Area, or a majority of them are. I think they're on the order of $15. If you do the mileage equivalent to gasoline, I think it's over twice as expensive. But techno-economic analysis I've seen is that just on scale alone, so the economy of scale, just making it, putting it everywhere, that can come down up to 50%. Just basing, if everyone were able to just flip a switch and then get on a hydrogen tomorrow, that cost would be almost pretty much cut in half. And then you're looking, and hopefully in technological advancements to bridge the rest of that, whether it be technological advancements in hydrogen fuel cell cars or in hydrogen production. And then hopefully we can get it even lower to be on par or better. But it's hard to unseat fossil fuel and internal combustion engines, because right now they're the cheapest technology out there.
Got it. All right, Julie, one question for you. So somebody, it sounds like, wants to do some science experiments. If they wanted to get their hands on a kit to work on at home, how would they get started? Can somebody make, for example, that electrochemical sandwich that you showed earlier with items that can be found around the garage?
Yeah, so that's a great question. And there's a great New York Times article actually about a guy who kind of makes hydrogen on his own and has a hydrogen fuel cell in Massachusetts. If you Google New York Times hydrogen guy, I think it comes up actually, to be honest. But The electrochemical sandwich might be a little hard to do at home, to be honest, only because the membrane itself is really expensive. So DuPont, the chemical company, was able to make this membrane many years ago. And the reason why it's so hard to make some of those other electrochemical sandwiches in more basic conditions is actually because it's really hard to transport these ions through. So they got really lucky. So that would be a little cost prohibitive. And also with the electrochemical sandwich I use, it also uses really expensive catalysts. So platinum is one of them. So that would be a little hard to do at home too. But if you are interested in, understanding hydrogen or trying it, looking up more on the basic side, so more alkaline conditions, you could use more of an electrolyte. So it's not a sandwich, but it uses a liquid, and you can use hydrogen that way. But as Arthur and I talked about with safety, I would definitely make sure all the safety at hands is making sure you're being very, very safe about this, since hydrogen is dangerous and it's a lot harder to capture that. But like science experiments, for instance, like I said, I did it for the after school hour at Berkeley, where we actually made a little bit of hydrogen using just salt water and spoons. So nickel is a good catalyst to use it, and you can understand that. So that's kind of where to start. Electrochemical sandwich, I don't think is cheap enough yet that people can start making it at home, sadly.
All right, so I'm going to ask a question for the both of you. How do both of you see hydrogen infrastructure evolving in the future? Planning, centralizing things, fueling stations, ad hoc distribution, tiny fuel cells, something else entirely. What do you see for our future?
So my opinion would be something that we're seeing now. It's related to just gasoline stations. That's what I see as like the next logical step. Because I mentioned on infrastructure is that they're focusing on high traffic lanes for commercial shipping and like container ships. So developing and growing from that. So I think centralized distribution is probably the next step for how it would look. Because number one, we're familiar with it. So then you got to go gas up your car. So that's where I see, and that's where a lot of the focus on developing the infrastructure is really growing from high traffic routes and then growing out from there. So I think the centralized thing is going to be at least in the next phase of this of hydrogen energy.
Yeah, I agree with Arthur on that. And I think in the next 5 to 10 years, I think hydrogen is going to find its place and grow like rapidly. So there's a lot of money from the bipartisan infrastructure bill that got passed last November on manufacturing and deploying. And so a lot of these systems for infrastructure that Arthur talked about is going to kind of go into those more traditional, what we're familiar with. But there needs to be a lot of innovation because, there's hydrogen that's used in ammonia to make fertilizer, right? So how can it fit in there? And that might be a little bit smaller type system. So there are a lot of startups that are coming up through the pipeline that are trying to figure out what are these small niche applications. And I think with more excitement, more investment to figure out and accelerate these technologies and deploy them, it's going to grow like rapid. So while I think Arthur and I agree on the centralized, I think there might be some really interesting decentralized, so very niche, small systems that'll be there. And we only talked about one type. There's lots of different types that could be used for housing, or it could be used for more like data centers, for instance, and things like that.
Awesome. Thanks, guys. So Julie, for you, would the catalyst used for H2 generation utilize some of the very rare metals like palladium and rhodium? I had to look those up because I didn't even know what those were, that are also currently used in smog reducing catalytic converters for cars and are mined in politically sensitive areas of the world. So is that something that we should be thinking about, or that's already being thought about?
Yeah, it's definitely already being considered. So we are in that platinum group metal area for at least this proton exchange membrane sandwich, we like to say, that Arthur and I use a lot. And so it uses platinum and it uses iridium. And a big part of what I work on and several of the postdocs that I work with, even more specifically, have looked at, okay, we have X amount of iridium available. Wait a minute, like we can't make these large systems anymore. Crap. So trying to reduce how much catalyst is actually something as scientists we're trying to understand. Can we make them just as efficient but using less? Plugging maybe what I'll be working on at the DOE, like there's initiatives for recycling. So that could be really interesting, that I'm really excited to see, how can we recycle some of these systems? But yeah, especially for different areas, I'm actually less aware of exactly where all of these are mined. I've like kind of gone into that rabbit hole, but then never found it exactly where. But that's something we all have to worry about when it comes to, scaling up these systems, is who are we affecting when we mine these systems, and being very, very sensitive. And I know that is a conversation because we've learned a lot from the battery community, with cobalt, for instance, of the practices that are happening right now is not great. So how can we learn? So, as hydrogen is growing and scaling up, how can we minimize those disruptions for like local communities and various different cultures and things like that?
Okay, so speaking of scale up, we got a question about grid scale energy storage. Is it likely that hydrogen and fuel cells could be used for grid scale energy storage? This is a major concern with renewable energy, that needs a solution, both in the short term and the long term. I don't know if Julie or Arthur, you have thoughts on that.
I definitely think it could be used. There's been talks of trying to use some pipelines, instead of using them for fossil fuels, using them for hydrogen. And that's one way where, you can make a hydrogen anytime. And then if you make a lot of it, you could store it. As Arthur and I mentioned, we are not the storage experts here. So we're not really exactly sure the logistics of making sure that it's safe, like with all the leaks. It's an active area of research that many people are working on. But I think it could be really helpful in that, a battery discharges, I'll pick up my Kindle and be like, oh no, like what happened? I need to charge it again. Where hydrogen, as long as we can trap it and keep it in a tank, in either the absorbent or, just a large tank, then we'll be able to get electricity. So that would be really helpful. And that's kind of the study I showed too, is like, people have looked at, okay, how can we use this in a way that can help, maybe during natural disasters when you can't access the grid. And that is one way that hydrogen, I hope that that's one way hydrogen can really help. I might be optimistic, but that's really what I could see as helpful, because we're not dependent on, material limitations. We are dependent on how much we store.
Thanks. So let me ask a couple questions just about just taking a step back about hydrogen. So you both mentioned earlier that companies like Toyota and Hyundai and DuPont are operating in this sort of hydrogen generation and application space. Are there other companies who are looking at hydrogen? So that's part one of my question. And the second part of my question is, where does the US sit in relation to other countries who might be investing in hydrogen infrastructure? What countries might be farther along than the US in the use of hydrogen fuel cell energy?
Okay. See, there are several other, like I think Bosch is a German company. They're big into it. There are other companies. Nel Hydrogen is another one, and there's also a lot of startups associated with it. But there's a lot of there's a growing number of players in the hydrogen game in commercializing this technology, and I really believe that the U.S. is pretty close to front. But in my opinion, I think some of the European countries, Germany, I think Netherlands and stuff like that, really are have a strong push as well. And I think and that's just my observation about what I see in productivity and production. I forgot what country that they installed a plant scale electrolyzer plant, and they're operating it over there as a hydrogen generation source. So I think I see Europe as a growing player that may be a little bit ahead or maybe just more eager to get onto this hydrogen as the next gen fuel source.
Yeah, and just to add on, companies like Shell are also getting in on this because they're starting to realize that it's important for a lot of their processes. So how can they decarbonize? I also am aware of, it slips my mind the name, but there's a big wind turbine company in Denmark that is like, oh, wind turbines, hydrogen, let's figure out how to make it. And Siemens is another big one. So like a lot of companies we know and we hear about actually have a hydrogen component and it's growing. And like Arthur said, there's a lot of startups coming up out of the woodwork in the Bay Area, in Boston, things like that. And yeah, I would agree with Arthur. Europe has been really aggressive in the last couple of years of putting hydrogen into their like energy plans. So Europe has been really aggressive of how can we use hydrogen to as a source and as a resource. And there's a lot of companies coming out of there too that are growing immensely in the hydrogen space.
Got it. Thanks both. All right, I'm going to get a little technical now because we've got a couple technical questions. So Arthur, when you're talking about modeling, somebody wanted to know what metrics you're using in the experimental comparison process that you described for optimizing the models that you use.
So so how I compare experimental and my simulation data. Some things are really very hard to assess. Like I showed a heat distribution or a temperature map. It's very difficult to pinpoint temperature at every point inside our system. So those type of analyses are very hard to detect. But overall performance, one example is pretty much the direct most output that we something we call a polarization curve. It's like how much electrical potential that we generate or how much power can we generate at a given current. Pretty much my goal is to, because all the physics that I develop try to simulate what's actually going on or what we believe is going on in a fuel cell. So I'm able to generate mathematical simulations that try to replicate what we see experimentally. And then that's what I say is like, so I do also things like statistical analysis to make sure that like, all right, are these statistically within agreement? Can I mathematically and justify say like, oh, this represents this system. So there's a math component of that to say that because like it's not just an arbitrary, it's like, oh, it looks like it, and it looks like it's doing it. So the metrics that I use are often statistical in trying to compare experimental data versus simulated data. And then, at that point, there is a certain amount of assumptions, and then we rely on a lot of other type of disciplines in order to have a certain amount of confidence in, like, so the chemical reactions that are occurring. We don't have a microscope that can zoom in and see the chemical reaction, say, oh, that's what's happening. And then, so a lot of it we have either lab data analysis or even like, data from actual implementation, in actual larger scales. And then we tailor those models to represent what we think is going on. So a lot of math behind it and a lot of statistical analysis, which I try to bake into the type of modeling work that I do.
Got it. Thank you so much. Julie, technical question for you. Somebody wants to know what the best method is to separate hydrogen from oxygen after electrochemical water splitting.
So ideally, it'll already be separated. That is the goal if you don't want it in there. And so with our electrochemical sandwiches, the hydrogen will happen on one end and the oxygen will happen on the other, and that never sees each other. And that's like really important because then you don't have any mixture. So then it's not any kind of mixture of gases that can potentially explode. The way to do it in some of the systems that uses a liquid electrolyte, I will be honest, I'm not actually sure. That's the funny thing of when you're a specialist and you're like, wait a minute, how do they do this? So that's a really good technical question that I'm not 100% sure on. But for our systems and a lot of systems, they try and keep it as separated as possible. So then the oxygen can go into the water, and then the hydrogen, you can just store it straight into a tank, for instance, and they never see each other, because then that can lead to some safety concerns.
Great, thank you. So somebody says, I worked with combustible gases in the past. How do you monitor the H2 concentrations around your system to keep it below LEL, which I looked up is lower explosive limit? So how do you monitor your concentrations to keep it below that limit is the question.
So normally we make sure before we're even operating anything in our systems, everything is as tight as possible, so there aren't any leaks. So we do leak tests with as minimal combustible gases as possible. So that's like number one. Number two, then we can have typically a gas monitor around, so we can make sure there's no gases when we're operating. But we do have an idea of if our cell is operating at X amount of current, right? We can then do some math to calculate how much hydrogen is that going to be. And a lot of the labs have a large exhaust, so the displacement, so the movement of air through helps dilute that hydrogen a lot. So depending on how big of the size we have, that's kind of where we can change how much we have, the safety controls that we have around it. Additionally, we have combustible gas detectors that are around to make sure that nothing is going to happen there either. And I've seen even other systems, especially more automated systems, where they'll have automation to shut off the hydrogen if they detect any kind of like hydrogen leak outside of the system as well. So there's lots of controls to prevent it. So it's not reaching the limit. But early on in my PhD, that worried me. Don't you worry.
I'd be worried too. Arthur, do you want to say something?
Oh yeah, I think the only one that I had, she covered almost all of it. And the only thing that I would add is that at least in the lab scale, also we do a lot of pressure testing with our equipment. And so we don't put hydrogen when we're pressure testing. We use inert gases that won't cause anything, but you pressurize them well beyond what they're what we're going to operate, but still within design limit of the physical equipment. And you just make sure that you have no leaks on our existing. So then there's another safety protocol. Just we pressure test all our gas supply lines and our equipment to make sure that we're not leaking hydrogen, because a small leak can build up and can put us at risk. And then she said we have outside, like hydrogen detection systems as well that will alarm and shut everything down if we have those issues.
These are really great questions, because I know the public can often be concerned with, what's the scary science going on in the labs. And so it's nice to know that there's so many precautions taking place, both at Berkeley Lab and UC Berkeley. So thanks for putting us at ease, guys. There's another question a bit around at least the safety of the atmosphere, maybe. What's the status of CO2 alkaline fuel cell poisoning from atmospheric O2 use? Can either of you answer that? I would think that's an Arthur question. Are you aware of that?
Say it one more time, or is it in text somewhere?
Sure. It was in the Q&A at 12:54. What's the status of CO2, so carbon dioxide, alkaline fuel cell poisoning from atmospheric oxygen use? And we can skip that one if we're not. Okay, sure. I'm going to ask a question because we went through kind of more technical questions. We went through danger questions. So I'm going to ask a great question we like to ask all of our speakers. So we probably have some young folks in the room, or parents of young folks. And, you were talking about so much about math and statistics, and it got me thinking, what were your guys' undergrad degrees in? What were you interested? How did you even get to this space? So could each one of you answer that question of how did you end up in hydrogen fuel technology? What did that path look like for each of you?
I could start. Oh, well, I did see that I don't work in alkaline fuel cells. That's one thing in the response to that question. Okay. And I don't really know about alkaline fuel cells.
Good.
Primarily proton exchange. So I don't work in alkaline, so that I can't answer that question. But my path, undergraduate degree in chemical engineering, ended up working in industry for several years, and then then I wanted to do something more environmental. So I went and did my PhD, and my PhD advisor is an electrochemical guy by his training, and that's all his group worked in. I had zero experience with electrochemistry, so I was probably like more unaware of that field, and then just ended up working in his group and then developing as an electrochemical guy and electrochemical chemical engineer. And then so then my work is focused on utilizing electrochemistry for other applications. And then I came into contact with LBNL, my current boss, who's named Adam Weber, who also is a co-advisor to Julie. And then he just a different application of electrochemistry. So it went from being an engineer to wanting to do something focused on the environment and being something that develop solutions to some of these energy problems that we have. And then it grew up from there to where I'm at now.
Yeah, and then I also majored in chemical engineering in undergrad, but I actually chose material science engineering, had a research experience in the summer after my freshman year, and I had a great mentor who was like, chemical engineering is like maybe more useful, which might not actually be true at all. But that was his bias. And so he inspired me, and I looked at the curriculum for my program, and it was a little more, I was interested in plastics at that time. So I was like, oh, like that's materials. Everyone uses it. I can make an impact. Great. And so I switched to chemical engineering after that experience. But as you can see, I'm not doing plastics whatsoever anymore. And I kind of just took on different experiences and research because for one, I started realizing like, oh, the environment is really important and I want to take care of it. That might have been because I really loved outdoors. So I was trying to figure out how can my degree be applied to those types of systems. Additionally, I did about a 9-month-long internship at a company. And while it was really important for manufacturing, it was not anything for the planet. It was a big like manufacturing plant, and I just wanted to be kind of on the cusp of science. And that's really what a PhD does. So I chose to do a PhD. I chose it here actually after doing a summer internship program at Berkeley Lab, which I highly recommend because I love the SULI program, which is the Student Undergraduate Laboratory Internship. And that really helps, that had me meet Adam Weber actually. And he sold me on hydrogen. So I was like, okay, I guess I'm in hydrogen. But the path was a little curvy, figuring it out. And as you can see, I'm going to be heading into the Department of Energy. So won't be in the lab anymore, but it'll be a good experience to see, how do you make an impact on, more of the administration policy level, and scientists are needed there too. So that's kind of my path here, and I'm looking forward to the future within this field at least.
Wonderful. This was so great, both of you. We want to thank Dr. Julie Fornaciari one more time and Dr. Arthur Dizon one more time for this amazing presentation. Again, we will be emailing you the video of this recording, and I'm going to go ahead and just share my screen one more time about our upcoming programs. CRISPR, we will have some great talks there on July 21st, and Material Science for Sustainability. So save those dates and be on the lookout for those invites. Anything more from you, Jen, before we head off?
Nope, just thanks again to Arthur and Julie for their great presentations and for our audience for tuning in and asking such wonderful questions. We're looking forward to seeing you in July.
Yes, and you can go to both of our websites for more information about our programs, lbl.gov and science@cal.berkeley.edu, and stay tuned for many more things from UC Berkeley and Lawrence Berkeley National Labs. Thanks, everyone, and have a great rest of your day.
Thanks, everyone.